Okay, so we have question number 23. Let's see. Okay. The projectile suddenly explodes into two fragments with equal masses at the highest point P of the trajectory. If one fragment falls vertically downwards with an initial velocity as shown, which of the following diagrams best represents the path of the other fragment? Neglect air resistance. The broken line represents the path of the projectile if there was no explosion. Let's see. Right, so at the maximum height, this mass of m explodes and it becomes masses of m over 2 and m over 2. What happens to one of the m over 2's is that it goes downwards. So they have mentioned that this mass m over 2 goes down with the velocity of u. Right. Now you know something like this. Now before the explosion, the mass m has to have a velocity v like this at the maximum height. The mass of m, the total mass m, has a velocity of v before explosion. Right. And then the momentum of that mass is going to be mv in its direction. Is that clear? Right. Now, if you look at the system, now when the explosion happens, it breaks down into fragments, right? So the mass m becomes m over 2 and m over 2. But there are no external forces during the explosion. There are only internal forces during the explosion. Is that clear? Then, if there are no external forces and only if internal forces occur, that means the momentum should be conserved, right? Is that clear? So the momentum should be conserved. Initially, before the explosion, the mass of m has only a momentum in the x direction. Can you see that? The mass m has a momentum only in the x direction, and the value is equal to what? mv. That means it cannot have a momentum in the y direction after the explosion. If it did not have momentum before the explosion in the y direction, it's not going to have a momentum after the explosion in the y direction. It is the conservation of what? Linear momentum. So just see the beauty of applying the theory. It's just what you know already. So what you should do is to just apply the theory perfectly. First you've got to understand that really well and then apply. Application of a perfectly understood theory. That's what's necessary for physics. Right. This gives me a clue. Now, after the explosion, we know that one of the masses, m over 2, goes down vertically at a velocity of u. Then the other fragment, m over 2, which is the identical fragment, should definitely have a velocity of u upwards. Why? Why should it definitely have a velocity of u upwards? Tell me. Because the momentum in the y direction should be cancelled, right? So only if I have momentum of m over 2 times u downwards and m over 2 times u upwards will the momenta in the y direction cancel out. Therefore, I will only have momentum in the x direction, and that's what I need to have. I think it's pretty clear. Right. Okay. So, but also, like before the collision, sorry, really sorry, before the explosion, the momentum is equal to mv, right? Before the explosion, the momentum is equal to mv. After the explosion, the momentum should still be mv, because momentum cannot change, because momentum is conserved. Why is momentum conserved? Because there are no external unbalanced forces. That means the momentum of m over 2 can be written like this. M over 2 times 2v. Can you see that m over 2, this mass m over 2, should have a velocity of 2v horizontally. So it should have a velocity of 2v horizontally definitely, because when it has a velocity of 2v horizontally, only we can get what? A momentum of mv, which is equal to the previous momentum. And they have mentioned in the question that this mass m over 2 has only an initial velocity downwards. It directly falls down. I think you understood that. If it has a velocity of u upwards, like so, definitely it should be following a path like this and then falling, right? It should be following, it should be going up a bit should be going up a bit and then falling. Is that clear? Now you understood why you should take a path like this. So from that conclusion, we can remove answers. What answers can we remove? The first answer can be removed, the second can be removed, third can be removed. Fourth and the fifth have this idea, right? Okay. Now let's understand this further. Next thing that I'm going to apply is this concept of center of gravity. Now, the center of gravity of the object is here, right? Before the explosion, it's here. Will the position of center of gravity change after the explosion? No. The position of center of gravity cannot change after the explosion. Why? The reason is the position of center of gravity cannot change after the explosion because there are no external unbalanced forces. Therefore, there is no external unbalanced force to cause a delocalization in the position of center of gravity from the previous path. Okay, in simple words, what we mean is the position of center of gravity cannot change from the normal path that it has to follow because there are no external unbalanced forces causing it to change. I hope it's clear. So look at this. If you look at this, the motion of center of gravity should be like this. It cannot change because it's an explosion. The motion of center of gravity cannot change. But then, it's kind of a confusion, isn't it? The motion of center of gravity cannot change. But then the particles are going in different directions. So what can we do? Okay, now this is the path. This is the mass capital M, simple M, sorry. And it was supposed to go like this. But though it was supposed to go, it exploded. And you know, when it exploded, mass of m over 2 came to this position, right? Mass of m over 2 came to this position. Then the other mass of m over 2 has to come to this position. Is it correct? No. It cannot come to this position. If it comes to this position, the center of gravity would lie here. So it cannot come there. Center of gravity should be here. Therefore, where should I have the mass of m over 2? I should have the mass of m over 2 at a distance equal to this r, which is the previous range from here to here. Then I should have m over 2 here. If I have m over 2 here at a distance equal to this distance, only can I have the center of gravity here. Is that clear? So then, can you understand this mass of m over 2 has followed a path like this and then come here? Because if it follows a path like this and comes here, only I can find the center of gravity here. Because I need to find the center of gravity here definitely. Because I'm going to keep using the word collision. Though an explosion occurred, it occurred resulting in internal forces. There are no external forces. I think you understood this enough, right? Because, yeah, of course the momentum is changing. But you may be thinking, what external forces am I talking about? Other external forces apart from the external forces that are already there. Like, yeah, mg is already there, right? That's an external force. But what I'm talking about is there are no any other forces which are unbalanced except for mg. Is that clear? So what mg does has to be done, right? So this is the conclusion, right? I think you understood this well. Take your time again, and if you did not really understand this, you can go through this again and again. Rewatch the video, you'll understand it. Okay. Then we have to do question 24, right? Two thermodynamic processes, ABC and AC, of a closed system of an ideal gas are shown in the figure. In the process ABC, 6 kilojoules is absorbed by the system to go from A to B. So highlight from where to where? From A to B. So we need 6 kilojoules of heat to be absorbed to the system to go from what? A to B. And 1.8 kilojoules of heat is absorbed from B to C. So when you go from B to C, 1.8 kilojoules. When you go from A to B, you require 8 kilojoules, 6 kilojoules. 6 kilojoules to go from A to B, and 1.8 kilojoules when you're going from B to C, right? What is the change in internal energy in the process AC? Right, so if I draw this diagram, this is A, this is B, and this is BC, okay, and they're represented a path like this, okay, this is AC, right, and this is like 3, this is like 8, and this is like 2, this is like 5, right. What can you say? What is the change in internal energy in the process AC? Remember this, the change in internal energy in the process AC should be equal to change in internal energy in the process ABC, because my starting point is the same and my ending point is the same, and I'm also going in the same direction. What do you mean by direction? I'm going from a lower PV product to a higher PV product. I may be taking different paths, but my final destination and my initial destination are the same. So I'm coming back to the same PV products, right? So we know PV is equal to polarity, right? So number of moles here, I'm not changing number of moles, and R is a constant anyways. So if I come back to the same PV product, in whatever the path I take, if I come back to the same PV product, I have to definitely come back to the same temperature. If I come back to the same temperature, which it means that the same internal change occurs, internal energy change occurs, right? So that you understood. So if I can find the internal energy change of path ABC, I'm done. Then I've already found the internal energy change across path AC, right? Now let me know, right? How can I do that? I can apply delta Q equals what? Delta U plus delta W for the path ABC. So for the path ABC, I'm going to apply what? Delta Q is equal to what? Delta U plus delta W. You know this equation, right? Heat absorbed or released, change in internal energy, work done on the system or work done by the system. Right? Delta Q, when I go from A to C along the path ABC, what's delta Q equal to? Along this path AB, the heat absorbed is given, let's see, what's the heat absorbed? Heat absorbed is 6 kilojoules, right? And here the heat absorbed is what? 1.8 kilojoules. So a total of what? 7.8 kilojoules of heat is absorbed along the path ABC. So I don't know the internal energy change. What's the work done along the path ABC? That is covered by this area, right? This entire area. Because there's no work done here. When I go from A to B, there's no work done because there's no change in volume. You know, work done is equal to what? Pressure times delta V. If delta V is 0, if the volume change is 0, work done becomes 0. So then the work done is actually in the path A, in the path BC. In the path BC, only work is done, right? So what's the work done? Yeah, this is 3 and this height is 8. So the area. So I get 24. I'll be careful of the units. Here the pressure is given in what? 10 to the power 5 pascals. And here the pressure, here the volume is given in what? 10 to the power minus 3 meter cube. Here the volume is given in 10 to the power minus 3. You have to be very careful, right? Volume in 10 to the power minus 3 meter cube and pressure as 10 to the power 5 pascals. So then I get what? 3 times 10 to the power minus 3, the PV product, right? Times 10 to the power 5 times 8. Then I get 2.4 kilojoules, right? 2.4 kilojoules. Yeah, the answer is 2.4 kilojoules. Okay? We simplify. Right. Now then I should put 2.4 here. Then kilojoules. Right, so 7.8 minus 2.4 kilojoules was the answer. 5.4 kilojoules. But what is surprising is that in the exam paper, they have given this as all. That is an answer for everybody. It's a mistake. What's the mistake? Look at this. Right? Look at the path BC. Look at the path BC. What's the, let's see the equation delta Q is equal to what? Delta U plus delta W. Right. If you look at path BC, what's the heat absorbed? 1.8. That's kilojoules delta U plus. If you look at the path BC, what's the work done? Yeah, work done is equal to what? 2.4, right? Yeah, 2.4. Can you see delta U gets a negative value? No, delta U cannot get a negative value from here to here. Is that clear? Because internal energy has to increase here. So that's the mistake in the question. Delta U cannot be a negative value in the region BC, right? Because internal energy of the gas has to increase. Think about Charles' law, right? The pressure remains constant, but the volume increases. Then the temperature should increase, right? So next we have to do, question number 25, right? So 3-point charges plus Q, plus 3Q, and minus Q are placed at the vertices of an equilateral triangle of side A as shown in the figure. So read the question very well. The electric potential energy of the system is given by. The electric potential energy of the system is given by. So let's see. So I have plus 3Q here. Plus 3Q here. And I have plus 4Q here. Plus 4Q here. And I have minus Q here. So plus 3Q here, plus 4Q here, and minus Q here, right? Okay. Think about this. What's the electrical potential energy of the system? And they have given this to be A, this as A, and this as A as well, right? So it's an equilateral triangle. What you should do is to first pair them up. Just think about these two first. Find their electric potential energy. Think about these two then. Find the electrical potential energy. Think about these two then. Find the electric potential energy and add them up. But remember, now electrical potential energy is equal to what? W is equal to what? 1045 epsilon naught if it's the vacuum. Epsilon naught if it's vacuum, otherwise epsilon. Times the charge Q1 times Q2 divided by the distance. If I have charges Q1 and Q2, right? The distance of R, the potential energy, electrical potential energy is equal to what? 1045 epsilon naught times Q1, Q2 divided by R. Okay, same idea. And remember, this equation is charge sensitive. If I put positive here and positive here, the answer is positive. If I put positive for Q1 and negative for Q2, the answer is negative. So remember that. Okay. Right, look at these two first. What's the potential energy of the system? 1045 epsilon naught 4Q times 3Q divided by A. It's positive. Right. This is W1. What's W2 equal to? 1045 epsilon naught 3Q times minus Q. So I get what? 3Q minus Q divided by A. What is W3 equal to? 1045 epsilon naught 4Q times minus Q divided by the distance between them, A. So you can easily simplify. This is a negative answer, this is also a negative answer, right? So I can take Q squared over 45 epsilon naught out, and I'm adding W1 plus W2 plus W3. So I get what? Q squared over 45 epsilon naught is out, and then here I have 12 minus, here I have what? 3 minus, here I have what? 4. Then I have what? 5Q squared over 45 epsilon naught times A. Forget A is also common, right? This area A, this length A is also common, right? That clear? this length A is also common. I think you understood this. So Q squared over 4, 5 epsilon naught A is the common factor. Right, got it?